Now we will study some special purpose diodes. First one is varactor diode. See, varactor diode is used in the circuits as a capacitance. The fabrication process and the material used ensures that the variation of capacitance from C minimum to C maximum will be maximum for this diode as compared to normal PN junction. If we are using a varactor diode, then we can ensure that the capacitance variation in diode, if we vary the voltage, biasing voltage will be very large as compared to other diodes. This diode is normally a linearly graded diode. If it is a linearly graded diode, for this the transition capacitance CT will be inversely proportional to cube root of reverse bias voltage. Earlier we have seen this diode is always used in reverse bias. If we are using in reverse bias, the capacitance will be transition capacitance. Application of this diode. Application of this diode. First, it is used in tuning circuits, in radio receivers. It is used for fine tuning of radio receivers. Number two, it is used in parametric amplifiers, where it is used for amplification of high frequency signals. The varactor diode is also called with different names like varicap, voltacap, means voltage variable capacitance. Means we can vary its capacitance by varying the voltage. We can change its capacitance by changing the voltage. So it can be used as a voltage variable capacitor. The next diode is light emitting diode. Light emitting diode is another type of diode which is used especially for as a light source in optocouplers. In light emitting diode, operation is simple. If we forward bias this PN junction, we will make sure that it is fabricated from direct bandgap semiconductor. Earlier we have seen what is direct bandgap semiconductor. In direct bandgap semiconductor, if there is any recombination between electron and hole, the energy will be released in the form of light. So we will use direct bandgap semiconductor for this PN junction. In this PN junction, this is P side and this is N side. If we bias in it in forward direction, then the majority charge carriers holes from P side will be injected to the N side, and majority charge carriers on N side will be injected to the P side. When these majority charge carriers cross the junction, then in this particular region there are large number of recombination of these charge carriers, and due to these recombinations light will be emitted by this diode. So principle of operation for this diode will be electroluminescence. Means we are getting illumination by supplying electrical energy. So this diode is illuminating when we supply a forward bias voltage to it. Second important point about this diode, it should be always used under forward bias. We cannot use this diode in reverse bias, because in reverse bias there are no charge carriers available to cross the junction. Yes, there are some minority charge carriers which cross the junction and will constitute a very small current, that is I naught, which is the number of charge carriers in reverse bias are not sufficient to emit significant light. So it should be always used in forward bias. Number three, if we bias up an LED, then we should ensure that the applied voltage or the voltage drop across this diode VD should be approximately 3 to 3.5 volt. The typical voltage is 3.3 volt. For this voltage, this LED emit light of maximum intensity. And also at this bias voltage, the current through diode IF should be equal to 20 milliamperes. If current is 20 milliampere, then we can ensure that the intensity of light emitted will be largest. If current is less, intensity will be less. So if we are biasing an LED, the current through diode must be 20 milliampere and voltage must be around 3 to 3.5 volts across this diode. Now application of this diode. This diode is used as a source in fiber optic communication. Also, it is used in optocouplers. Fiber optic communication is an example of optocoupler itself, and already we have seen this LED in our remote control of TV. It is used in remote controls. So these are the applications of light emitting diode LED. Now we will discuss something about the color of light emitted by the LED. The color of light emitted by LED depends on the forbidden energy band gap of the semiconductor material used. If we are doping this semiconductor with some other doping, for example phosphorus, arsenic, these are dopants. If we are doping this material, then the forbidden energy band gap is varied little bit. Means if for a gallium arsenide LED it is 1.47 electron volt at room temperature, then if we are doping this material gallium arsenide with other some dopant, then this energy band gap will be varied little bit, and the color of light depends on this forbidden energy band gap. The wavelength of emitted light is given by h into mu, which is frequency. This term is frequency, divide by forbidden energy band gap, which is in electron volts. This term is called Planck's constant, and solving all these by taking it as frequency of light, then we can calculate. Sorry, I made a mistake. The wavelength of emitted light, we can directly write the equation for wavelength of light as the wavelength of emitted light is given by 1.24 divided by forbidden energy band gap of diode semiconductor materials. This energy gap will be in electron volts and this wavelength will be in micrometers. The equation in this equation, the Planck's constant and frequency, all these term are values are put and calculated, and this is the final expression we can use for solving the problems. Now, if we want to calculate forbidden energy band gap by seeing the color of light, then forbidden energy band gap can be calculated as Eg equal to 1.24 divided by lambda, which will be in micrometers. This equation can be used by seeing the color of light and to calculate forbidden energy band gap. Now, the color of light, by seeing the color of light, we can determine the wavelength lambda. The range of lambda for visible light is from 0.38 micrometer to 0.76 micrometer. If the wavelength of emitted light is in this range, the light will be visible and we can see this light. This is the wavelength of red color and this is the wavelength of violet color. And if lambda is less than this 0.38 micrometers, light will be in ultraviolet region. And if the wavelength of light is in this region, above this wavelength, then the light will be in infrared region. So if visible light is emitted, its wavelength will be in this range 0.38 micrometer to 0.76 micrometers. Now we will calculate, solve one problem. Calculate the energy band gap of semiconductor material used to fabricate an LED which emits light of wavelength 5490 angstrom unit. So we have given wavelength of light and we want to calculate the energy band gap of the semiconductor material used. We know the relation lambda equal to 1.24 divided by Eg, forbidden energy band gap. From this equation we can write Eg equal to 1.24 upon lambda. Lambda is given 5490 angstrom unit. This can be written as 0.5490 into 10 raised to power minus 6, as angstrom unit equal to 10 raised to power minus 10 meters. So converting, we can write it as 0.5490 micrometers, which is required to be substituted in this equation. Lambda will be in micrometers. So forbidden energy band gap Eg will be equal to 1.24 upon 0.5490. This will be in micrometers, and the forbidden energy band gap will be 2.26 electron volts. Now, the third type of diode will be photodiode. Photodiode is used to sense the light which incidents on it. This photodiode has one fabrication property, that its doping level on P and N sides are very low as compared to normal PN junction. The depletion layer width W is given by twice epsilon upon Q into 1 upon Na plus 1 upon Nd into V naught, contact potential V naught. From this equation, we can easily see that these two terms are in denominators. Na and D are in denominators. So depletion layer width W is inversely proportional to doping concentration, root of doping concentration. If doping concentration is decreases, the depletion layer width increases. Same is the case in photodiode. In photodiode, the depletion layer width is very large as compared to normal PN junction. And also this diode is operated always under reverse bias. This is P region and this is N region, and this battery is making this PN junction reverse bias. Now, a photosensitive material is applied, placed over this junction. This photosensitive material, sometimes it is cadmium sulfide, sometimes it is zinc sulfide, or any other material. This photosensitive material is placed over the junction. This photosensitive material is placed over the junction when light incident on this diode, the effect of light due to this photosensitive material will be uh, the effect of light will be considerable as compared to in normal PN junction. So if first case we take, if no light incident, then we will say that in this diode which is reverse biased, P region and region, as it is reverse biased, the current will be very low and the current I will be set at I dark. This will be dark current and it will be equal to reverse saturation current of diode. Second case, if light incident on this diode, then the bonds in this depletion layer will be broken, because in the form of light we are supplying energy to these electrons which are in bonding in this depletion layer. So after getting sufficient energy, these electrons will break the covalent bond and there will be large number of charge carrier generation in this depletion layer. If a charge carrier is generated in this depletion layer, we can say that now this diode will start conducting and the current I will be equal to I dark plus I photon. Photon current will be the current through due to light incident on it. So now I can say that I photon, which is current due to light, is sufficiently large as compared to this dark current, because it will be in nanoamperes for silicon and in microamperes for germanium. So I is directly proportional to I is nearly equal to I photon. So when light incident on this diode, it will conduct. Applications of this diode. This diode is used in lux meters, which are used in during cricket matches to see the light. Number two, it is used in TV. In the TV, it is used to sense the light which is emitted by the remote. Next is tunnel diode. Tunnel diode uh, is bit different from normal PN junction. The first and main difference is doping is very high. It is a highly doped PN junction. In normal PN junction, the doping concentration is around 1 is to 10 raised to power 8 or 1 is to 10 raised to power 9. This is the doping ratio, means in every 10 raised to power silicon atom, one phosphorus atom is added. This is doping ratio. But in tunnel diode, the doping ratio is around 1 is to 10 raised to power 3. Earlier, just now we saw that depletion layer with W is inversely proportional to root of doping concentration. If doping concentration is increased, the depletion layer width W will decrease. So in this diode, the depletion layer is very thin as compared to normal PN junction. This is P and this is N type region. If we forward bias this diode, then the depletion layer will have a very less effect on the majority charge carriers, and the majority charge carriers cross the junction even for a very small applied voltages at a speed of almost light. Speed of light. These electrons will penetrate this depletion layer with almost at a speed of light. So this behavior of electrons is called tunneling, and due to this tunneling effect, this diode is called tunnel diode. So in tunnel diode, the doping is very high, and due to very high doping, the depletion layer width is very thin, and due to a very thin depletion layer, the electrons even for small applied voltages cross the penetrate the depletion layer almost at a speed of light, and this behavior is called tunneling, and due to this this diode is called tunnel diode. Now we will see VI characteristics of diode because it is important from examination point of view. These are the VI characteristics of a tunnel diode. As we can see that this in this diode, if we apply small positive voltage, the unlike normal PN junction, this diode is conducting. If this diode is conducting, we will conclude that for this diode V gamma equal to 0 volt, means there is no cut-in voltage for this tunnel diode. There is no cut-in voltage for this tunnel diode. For small applied voltages, the current through diode linearly increases with applied voltage. So we can say that it is operating in linear region or ohmic region. Linear region or ohmic region. And the voltage at which the current is maximum is, is called peak voltage, and the corresponding current is called peak current. And after that, the current through diode decreases if voltage is varied above Vp and a minimum current is obtained again. This minimum current is called valley current, and the corresponding voltage is valley voltage. And after that, it follows an exponential curve like normal PN junction, so it operates in exponential region. Now, in this particular region, if we want to calculate the resistance of diode, we will take 2 points. As earlier we have calculated the resistances diode. This is change in current and this is change in voltage Vd. Now if we calculate dVd upon dIf, it will give the value of resistance of this diode. Now in this particular region, uh, I will take this as point 0.1 and this as point 0.2. We can see that at point 0.2 the voltage is greater than the voltage with respect to point 0.1. So V2 minus V1, if I take change in Vd, so it will come positive. If I measure the current corresponding to point 0.1 and corresponding to point 0.2, then I can clearly see that the current at point 0.2 is less than current at point 0.1. So I2 minus I1 will be negative. And if we calculate the resistance, it will come out to be negative. If the resistance is negative, means with increase in voltage, if current decreases, this diode exhibits negative resistance characteristics in this particular region. And this diode is always operated in this negative resistance region. Negative resistance region. Always operated in this negative resistance region. So up to now we have for these diodes, depending on its type, different symbols are used to use these diodes in circuits. First, varactor diode is used with this symbol in the circuit. This symbol is used for varactor diode. Capacitance is shown with the diode. Light emitting diode is shown with this symbol, that light is emitted by this diode. And photodiode is used with the symbol, that when light incident, this diode will conduct, otherwise this diode will not conduct. This diode will always be used in reverse biased, and this diode will always be used in reverse bias, because we will get conduction only if light is incident, and this diode is used, it's in this diode we use its transition capacitance, which is only in reverse biased. And this diode in which is operated in forward bias, and recombination are necessary, and for this large number of charge carriers should cross the junction. And next, studied tunnel diode, it is used with symbol like this. These are anode terminals of all the diodes, anode and cathode terminals. And this tunnel diode is also used in forward bias and negative resistance region. Always operated in forward bias and negative resistance region. Now we will see an important diode, important from the examination point of view, that is Zener diode. Zener diode is fabricated with little higher doping. For normal PN junction, doping is around 1 is to 10 raised to power 8 to 1 is to 10 raised to power 9. And for Zener diode, doping is little bit higher. It is around 1 is to 10 raised to power 5 to 10, 1 is to 10 raised to power 6. This much doping is used in Zener diode, and a Zener diode is always operated in reverse bias in breakdown region. Now we will see what is breakdown. First, we will decide which material should be used for Zener diode. For Zener diode, its characteristics will be like this, and this will be breakdown region. So we are willing to operate in breakdown region, so we will choose a material for which its reverse characteristics will be according to the requirement. Two materials are there which can be used, germanium or silicon. If we are using germanium, then we will obtain this characteristics, this type of characteristics when it is operated in reverse bias. This is breakdown region. This is from here. This is breakdown region. And if we use silicon diode, silicon material, then the characteristics are like this. We can see two differences between these two characteristics. These are the characteristics with germanium, and these are the characteristics with silicon. One is the current, reverse saturation current for silicon, and reverse saturation current for germanium. There is large difference between reverse saturation current. We expect that a PN junction does not, should not operate in reverse bias. So that is, the current, reverse current should be equal to 0. But in both the cases current is not 0, but in silicon it is approximately 1000 times lesser than in germanium. This is the one advantage with silicon material. And another one is that in germanium diode, the increase in current, this is current axis and this is voltage axis. The increase in current is increasing in this particular part. This increase in current is gradual. In reverse bias, in this particular region, this diode is not operating. Only a reverse saturation current is flowing through diode, and now the current is increasing, means diode is entering into breakdown. This breakdown we can see is gradual. But if we take silicon diode, then in the characteristics I have shown that this breakdown is sudden. And when we operate a Zener diode in reverse bias, in the circuit it is expected that the Zener diode should have a sudden breakdown, which can be obtained only with silicon diode, cannot be obtained with germanium diode. So these two are major advantages of silicon material over germanium material. So we will use silicon diode to fabricate, silicon material to fabricate germanium.